Hi, good afternoon, all. Sorry, good evening, all. Um, so today we will be looking at assignment number 6. I will share my screen for that. Uh, I hope that you can see my screen. Uh, so we'll be looking at some of the typical problems of assignment number 6, and this assignment deals with the load flow studies, basically bus networks and all. So let us start with the first problem. Here, so the first question, it says that a 3-bus power system is shown in the figure below, this figure, where the diagonal elements of Y bus matrix are Y11. Hi, good evening. So we'll be looking at assignment 6 today. Could you just raise your hand and let me know whether you are able to see my screen?
Visible. Screen is
Hello.
visible, sir.
Okay, fine. Yeah. Okay. So we'll be looking at assignment 6 problems today, and this assignment mainly deals with the load flow studies. So let us first look at the first problem. So a 3-bus power system is shown in the figure below, this figure, where the diagonal elements of Y bus matrix are Y11 equals to minus J12 per unit, then Y22 is minus J15 per unit, and Y33 is minus J7 per unit. So they have told us to determine the per unit values of line reactances A, B, and C, which is shown in the figure. Now, for this, we need the knowledge of bus admittance matrix, which is given by this. So, since this is a 3-bus network system, we have this 3 cross 3 matrix. So, Y11, Y12, Y13, and so on. Now, so capital Y11 is the sum of the admittance Y12 and Y13. So admittance is just the inverse of impedance. So 1 by Z12 and similarly Z13. So now we know the value of Y11, which is minus J12, right? And Z12 is the admittance between bus 1 and bus 2, which is JA. I have written here JA, and Z13 is JB. So okay, so the first equation turns out to be 1 by A plus 1 by B equals to 12. Similarly, Y22 would be the sum of the admittance of Y21, that is between bus 1 and 2, and also between bus 2 and 3, that is Y23, which is again 1 by Z21 plus 1 by Z23. So we replace the values here. So Y22 is minus J15, and similarly in this way you get the second equation, which is 1 by A plus 1 by C equals to 15, which is your equation 2. Similarly, Y33 is given, the value is given, which is minus J7, and it is the sum of the admittance between J1 and Y31 and Y32. Again, this is inverse, so 1 by z31 plus 1 by z32. So in this way, we get our third equation. So we have three unknowns A, B, C, and we have three equations. This equation 1, 2, and 3. And they have told us to determine the reactance value A, B, and C. So if you solve this three equations, it comes out to be A, which is 0.1, B is 0.5, and C is 0.2, which is your option number B. So this was a pretty simple problem, I hope. Provided you know what is bus admittance matrix, provided you have gone through the videos of this pertaining to this assignment. So if you have any doubts regarding this problem, you can ask. You can just unmute and just pick up. So if you don't have any doubt, we will proceed to the next problem. So this is in this kind of assignment, we will be going through some typical problems, since we possibly won't be having the time to go through all the problems. So hence, we'll be taking up some good problems of every assignment. So now coming to question number 3. Here they have mentioned that a bus power system network consists of three transmission lines, the bus admittance matrix of the uncompensated system. So I'll come to what is uncompensated and what is compensated. So now this is the bus admittance matrix. Now let us try to draw the diagram of this kind of diagram, the bus diagram pertaining to this uh, admittance matrix. So I'll be using this screen here. So this is the bus network which has been given to us. So let me just copy this, minus J7, J4, and J5. So let us just copy this J7, this is J4 and J5. J4, J5, then this is J4, J8, and J10. And the third row is J5, J8, and J11. Now, the bus matrix is generally represented as Y11, Y12, and Y13. Then this is the second row is this Y21, Y22, and Y23, and this is Y31, Y32, and Y33. Now, just a second. Yeah. Okay. So now your Y11 would be the sum of Y11, which is the admittance corresponding to that bus, the Y12, which is the admittance between bus 1 and 2, and also Y13. Your Y12 would be the negative of Y12. Anyways, Y21 and Y12 are same, and also Y13 would be the negative of small y13. In the same way, we again have y22, which is y21, y22, and y23. Again, y 1 2 1 would be equal to y 1 2, which is equal to minus y 1 2. You can also write it as minus y 2 1, no problem. Similarly, y 1 3 sorry 2 3 it would be minus y 2 3. Now your y 3 3 would be y 3 1, y 3 2, and y 3 3. And y32 would be y23 itself, which would be minus y23, and so this is y31, right? This would be y13 itself. So now let us put all the values here. Sorry, your y11 is minus j7. So y11 is okay. We have the matrix here. Y11 is minus j7. Again, I am directly replacing writing small y12, which is minus j4, and y13 is minus j5. Right, now we can just replace the values here. Y11, so just putting the value y this equation, so y11 is y11 plus y12 plus y13, and we also have the values over here. So and this is j7, so this comes out to be j2. Similarly, so this I solved for finding out y11. Now you can also in the same way find out y small y22. So this would be, so y22 would be minus j10 plus j8 plus j4, so j2. And also your y33 would be j minus j11 plus j8 plus j5. Again, this is j2. Now we have all the values. We can now draw the this bus network. So this is your bus 1, this is your bus 2, and this is your bus 3. So we know we have the value of y11, right? So y11, y22, and y23. Now this represents the shunt elements, and you can from the value you can see, so y11 is j2, so z11 would be minus zero point 0.5, right? Minus j 0.5, and any impedance with a negative sign represents capacitance, as we know. So this would be something like this, since there is a minus, and for every this thing, every bus there is a shunt element, so we can draw something like this, which is having a value of minus j 0.5. So this is the per unit impedance, mind you, and what we are writing here, this is the per unit admittance. So while drawing the bus diagram, we have to use impedance only, and then we can draw the impedance between each and every network. So this is 1 2 and 3. So your y12 is what, minus j4. So y12 is minus j4, then z12 would be 1 by y12, so j 0.25. So this is a impedance, right? This is a impedance, so this is your j 0.25. And the y13 is your j minus j 0.5. So this would be again an impedance, which is between, sorry for my diagram, so this is j 0.2. And also lastly there is a impedance between this also. Not impedance, I mean reactance actually, not impedance, since there is no resistance. So J minus J5 Y13 is, sorry, Y, what is Y23? 1 minute. So Y23 is J8, right, minus J8. So this would be J1 by 8, which would be 0.125, right? J 0.125. So this would be the diagram, your bus diagram. And this is just for your convenience that I am drawing here. So I hope this whole thing was clear to you.
Yeah, yes.
Yeah, okay. Now going back to the question. So we see that, so this is the diagram of a uncompensated system. If you see the question, so the bus admittance of the uncompensated system. Now they are saying ki, if the shunt capacitance of all transmission line is 75% compensated. Now you may ask that what is your compensation, right? What is the meaning of this? So I will briefly try to explain it here, since the problem is connected with this term. And anyways, we will be revisiting this term later, while we will be, hopefully there is an assignment on voltage control. So we will be revisiting this concept. So you know that any power system network, it experiences widely varying conditions like no load, when the IR is 0, then overloading condition it also experiences, and also it experiences short circuit conditions mainly during your fault. So this also we will come, this is a very important concept in power system. So now in each of these conditions, the desired outcome would be that the quality of the power system, your quality is maintained. It is maintained. Now quality means your receiving end voltage and also your power factor. These two things are maintained. So this voltage is a very important thing, because you know, if there is a voltage variation, you may have some flickering in your tube light or while you are watching TV. So that is why your VR, the receiving end voltage control, or it being constant is very important. And also the power factor, since your power is Vi cos phi, so you can I mean easily see that if your power factor is low, the actual power that you get would be really very low. So that is why maintaining these two parameters are really very important. So now this voltage variation, this so as I was talking, so this voltage variation delta Vr, this mainly depends on the VAR, so the reactive power of the line. Now so the, as we know that the transmission line composes of inductance and capacitance, so it delivers a proportion of, some proportion of reactive power. Now it may not be useful to us, but it is really useful to maintain the quality of the line. So how, let us see by a small example. So let us consider a transmission line, a very simple transmission line. So this is the sending end, and this is your receiving end with a load, right? So this is, let's say this is V1 and this is V2, and let us consider that the line is purely inductive, so R is 0. And the current flowing through this line is, let's say, I, and the power, the apparent power being delivered is P plus jq. So we can write the equation. So V1 would be your I plus jx, right? V2 plus, sorry, V2 plus jix. So V2 would be V1 minus J Ix, and also this the power, the apparent power being delivered from the sending end would be, so this, since this is a star, so we had seen earlier, so this would be P minus JQ, right? Because we are considering the apparent power, and apparent power is given by this formula only. uh, so your I would be P minus JQ by V1 star. Now if we just consider the this thing, the magnitude only, so this we can write it as V1 only, right? Now if I substitute this in your what here, yeah, in this equation, so I am substituting in here, so this would be what, V2 equals to V1 minus your J P minus JQ by V1 into X. So this would be this becomes your minus P by V1 X, and this plus plus becomes minus minus becomes plus, and JJ becomes minus again. So Qx by V1. So if I combine all the real terms, this would be something like V1 minus Qx by V1, uh, and we are left with this term, which is this. So this is the real. So now if we draw the phasor diagram of it. So for reference, so as you know that the sending end voltage V1 is always constant, right? So and it is generally taken as a reference since that is a constant. So this would be your V1. Now we have this negative term here, which would be reducing the some magnitude of V1. So let us take it like this. So this would be Qx by V1, and there is a perpendicular term here since there is a J. So let us draw it like this. So this would be Px by V1, and its resultant is your uh, V2. So you can see that I mean the magnitude of V2, so it is far less than V1. So V2 is less than V1, and it's mainly due to this term, right? Because this is reducing, the V1 is being reduced mainly by this term. So that is why, and I mean V2 is less than V1. So now if I concentrate only on this term, so Qx by V1, you will see here that your X and V1, these are constant, but only thing is that your Q is varying, right? I mean Q is not constant because your line this thing, line impedance or reactance, whatever you say, this is constant, and also the sending end voltage is constant. So I mean in order to keep the voltage value, receiving end voltage value at a constant level, we should be maintaining this Q quality, I mean VAR Q. So that is why what is being done is that, and mostly these motors and also your television, everything, these are mainly inductive loads, right? So they do consume some kind of VR, since because these are inductive loads, so they do consume this reactive power. So that is why this Q keeps on varying in a transmission line, but we have to keep this Q constant in order to maintain the receiving end voltage. So that is why at the load terminal, so what is the diagram, yeah, at the load terminal, some kind of shunt elements are being added, no, normally. So these kind of things are called compensation. So what they do is that, so shunt element mainly means your capacitor or your inductor. So we will see that capacitor, it delivers reactive power, and inductor, it uh, you know uh, absorbs the reactive power. So for example, if a line needs a reactive power, we can connect capacitor to deliver that amount of reactive power to keep the receiving end voltage constant. And if a line has too much of reactive power which is bringing down the receiving end voltage, we can connect these shunt inductances. So this is what is being meant by compensation. So I hope this whole thing was clear. It was a bit lengthy, but still I want to try to explain. I hope this was clear. Okay. So now let us go back to the problem again. So that is why they are saying that it is 75% compensated. So the shunt capacitance. So we saw that these are capacitance only, right? We saw that the Y11, Y22, Y33, and Y22, all of these are capacitances only. So that is why it is already mentioned that the shunt capacitance of the transmission line is 75% compensated. So, and then they are asking that the imaginary part of the second row, second column. So as soon as they tell the second row, second column, we should directly concentrate on the second row itself, right? Because I mean, you will see why. So the imaginary part of the second row, second column element in per unit of the bus admittance matrix after compensation. So as you saw that we calculated anyway. So Y22 we found out to be J2. So after 75% compensation, so after 75% compensation means we are connecting an inductor here, and the net admittance is reducing by your what 25%, right? So it would be what 0.75, the J2 into 0.75, and it comes out to be J1.5. And hence now they are asking what would be the new bus, I mean, we new value of this Y22. So we know Y21 is J4 and minus J4, and Y23 is minus J8. And only the new value is this shunt capacitance, right? It changed to J1.5. So you just sum two. It comes out to be minus J10.5, which is your option number C. I hope I was able to make it clear.
I have a question here.
Yeah.
uh, Here it is shown it is 75 percentage compensated, right? So in that
Huh?
case, I need to change the value of y22.
Hmm.
It should be point 0.5, right? Because now the value is going to be reduced to zero point 0.5. That is one fourth is my the
Um,
existing value, right? Then it should be 1/4 instead of 3/4.
yeah, I mean, I also first initially thought of this, but no. 75% compensation means your this
I'm eliminating
shunt.
1.5
No,
from
no, no, no.
this
Listen,
one.
listen.
Yeah.
Shunt capacitance is reducing to 75%. Okay, it is reducing to 75%. Your 25% is getting deducted. I also initially thought this, and I checked on several textbooks and all. So this is what they are saying. 75% compensation means your shunt capacitance is reducing to 75% of its original value.
But
And
it is very clearly mentioned it is 75 percentage compensated. So if I'm taking J2 as the value, if it is 75 percentage compensated means then I need to subtract 1.5 or 3/4 from this value, which would be giving 0.5 J only to me. Because that is what means 75 percentage compensation, right? Here it is not mentioned 25 percentage compensation.
yeah, I know. I mean, I there is a confusion in this. Okay, maybe I'll try to get back
But
with
if we
this
try that
question.
option instead of J 1.5, if we make it 0.5 there,
Hmm.
do we have solution for that one? -4, -8. minus
So
12
this would
plus
be
0.5.
11.5.
Yeah,
Yeah.
yes. That's not in the list. Okay.
Yeah, that is not there in the list. Yeah.
Okay.
Yeah.
Here very clearly it is mentioned as 70%, 75% is compensated. So I guess I'm understanding right. 75% compensated in the sense I'm compensating the effect of capacitance for 75%, which is balance. I'll be having the effect of 1/4 of the actual value to J. That is what I'm understanding. Okay.
Okay, I'll try to get back. I mean, I'll look at some, look on the internet and also on textbooks more on this. But from what I got is that your when they say this line that it is 75% compensated, it means that your this capacitance is reduced to 75%. So I mean, it's 25% reduced. So yeah, I'll get back to. I mean, get back
Okay.
to you next week. You may also try to, while solving this assignment sheets of the current assignment sheets, if you try to get this problem, you can write to the NPTEL
Okay.
people. Yeah.
Okay.
So okay. So next problem number 4 is also a pretty interesting problem. So it is mentioned that your Y bus of a 9 bus system is 50% sparse. Now calculate the number of transmission lines of 9 bus system. So sparsity of a matrix basically means that some of the cells of the matrices are 0, right? So by the formula itself, we can say that sparsity means the number of 0 elements of the matrix divided by the total number of elements. Sparsity is 0.5, and let's say this is x and your total number of elements. So since this is a 9 bus systems, therefore this is a 9 cross 9 matrix, so total number of elements would be 81. So your x would be 40.5. So number of this is important. So the total number of non-zero elements would be what, the 81 minus this 40.5. Now you may ask that why we are subtracting 9 here. So if I take you back to this, so basically if you concentrate on the diagonal elements right here, so y11, y22 and y33, you saw that y11 is the sum of all the admittances corresponding to bus 1, right? And so these were all the admittances, I mean all the impedances that we drew here. So I mean this is the basically um, I mean what I can say, this is a transmission line, then this is also a transmission line. So while solving this problem, we can't consider this capital Y11 and Y22 and Y23 also, basically the diagonal elements, right, of this kind of matrix. So that is why, and in a 9 cross 9 matrix, we have a total of 9 diagonals. So that is why I'm subtracting this 9 from this thing, and this comes out to be 31.5. And now you can say that why are we dividing it by 2? This is very simple, because as you saw that your y12 is similar to y21, and your y13 is similar to y31, and also y23 similar to y32, equal to y32. So we only concentrate on the upper diagonal, I mean elements above the diagonal or elements below the diagonal. So since, as you can see, so since this was a three transmission line network, so between 1 and 2, between 1 and 3, and between 2 and 3, so there were three transmission lines. So as you, I mean looking at this matrix also, you can say that so y12, y13 and y23. So that is why you have to divide it by 2, and when you do that, it roughly or approximately comes out to be your 16, which is your option number D. I hope this was clear the way I explained.
Yes.
Okay. Now, again, there is some confusion with this. So let us first go through this problem. So a nominal pi circuit of a 132 kV three-phase transmission line is shown in the following figure. So this is a pi circuit transmission line, as we saw in the previous assignment. So they are saying ki find out the surge impedance loading SIL of the line where impedance is this Z equals to 80 and your X equals to 1000, 1 kilo. So as soon as you see this, so this is clearly mentioned that this X is you're nothing but the capacitance. Now your pi circuit line in a transmission line, it is generally represented by this, right? So this is the impedance and this is the admittance, right? So this would be what your y by 2, and this would also be y by 2, and this is your z. So the moment you see this, you remember what is the pi circuit diagram for a transmission network. So therefore you can write that this y by 2 is inverse to 1 by x. Therefore your y comes out to be 1 by 500. Now for surge impedance loading, we have to find the what is the surge impedance. So it is nothing but the square root of your impedance divided by the admittance. When you do this, it comes out to be 200 ohm. Now here comes the confusion. So surge impedance loading would be what your voltage, the this line voltage divided by what would be your this thing surge impedance. So when you do this, it comes out to be 87.12 megawatt. Now here you can see, so any for any three phase power, I mean three phase network, your power would be what 3 into the uh, phase voltage divided by the impedance, right? Now when I did this, so there was no three term here, so there was a bit of confusion in this. So I mean, anyways, when you do this, it comes out to be 87.12 megawatt, which is your option number D. So I had a bit of confusion in this. Uh,
I have a point here.
yeah,
Do we need to take y by 2 as one by how it is taken actually? Y
yeah,
by 2 should be y by 2 should be 500, right? Or 1 by 500.
no, y
Uh,
by 2 would be 1 by x, right?
Sorry, y should be equal to 1 by 1000,
No, 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 no.
and
What
y by
did I
2 should be
say?
equal to 1 by
Your
2000.
pi network is this, right? Y by 2, right? So each of this
But they
capacitance
have
is
given the value of x only, right? They have not given
fine.
value of
So here is the confusion. You don't
x
get
by 2.
confused. This is X, but
Oh,
this
okay,
is,
okay,
you have to
okay.
match this circuit with this circuit and then find out the
Uh-huh.
value of Y.
Okay, okay. Now I have not seen the drawing. Okay, I assumed
Okay,
the
okay,
pi
fine,
model
fine.
directly. Yeah, okay.
Yeah, yeah, you have to, I mean, keep this in your mind. This pi, or if it is a T network, what would be the T? So for T, it would be Z by 2, and then Y, right? So you have to keep that in mind. And
Yeah, it is clear now. Yes.
okay, so yeah, so let us go to problem number 7. This is a pretty simple problem provided you understood the previous problem. So here it says that the network shown in the given figure has impedances in per unit as indicated. So the diagonal element YY of the bus admittance matrix is what they have told us to find out, right? So Y11 would be what? This small y11, which is corresponding to this, then your y12 and also your y13, right? So y11, so your z11 is what? Minus j5. Then z12 is j0.05, and z13 is j0.05. Therefore, your y11 would be j0.2. You get your y12 as well, minus j20, and also y13 would be minus j20, since z13 was equal to z12. Now you just take the sum of this, since this is the summation of all the three admittances. You add this up, it comes out to be minus J39.8, which is your option number C. Pretty simple problem. I hope it was clear. Okay. Now, this is also another interesting problem, but pretty easy. So they have told us that the bus admittance matrix of a power system is given as follows. This is your Y bus matrix. Now they have told uh, the bus, find out the buses that are having the shunt elements. So as we saw that in this, where it was, yeah, this transmission network. So the each of these buses were having some shunt elements. Now shunt elements may be your capacitance also, as well as impedance. So in case of impedance, this would be plus, right? So yours, I mean, in case of shunt elements, your small y11 or small y22 or small y33 won't be zero. It would be having some value, be it positive or be it negative. Therefore, it is pretty simple. So your y11 is minus j.5. Your y12, small y12, mind you. So this is capital Y12, right? So small y12 would be negative of capital Y12, which is minus j7, and your small y13 is minus j3. You just take the sum of it. You find out that your y11 comes out to be j1.5. Now looking at, I mean, you can just see this bus admittance matrix and directly take out, I mean, do the problem. So if you see here, your capital Y22 is minus J18, and if you take the sum of this J7 and J18, you immediately see that it comes out to be plus J18, right? Therefore, you won't have any Y22, right? It would be coming out to be 0. In the same way, if you try solving this, so this would be what, y13 and y31 and y32 would be your j14, right? And your capital Y33 is j13, minus j13. Therefore your y small y33 would be j1. Therefore bus 1 and 3 do have shunt elements, and y22, since y22 is 0, number B. So pretty simple problem. I hope this was clear.
Yes.
Okay. So here it is. This is also a pretty simple problem, but this is a bit lengthy, since you have to find out this bus admittance as a whole. So they have shown us this diagram here. So this is bus 1 up till this point. This is bus 1. This is bus 2, and this is bus 3. Now clearly you can see that bus 1 would be having a shunt element, and also bus 3 would be having a shunt element, because since there is a capacitor and inductor connected to ground from bus 3 and 1. Therefore now I mean, you can write each element here. So z11 is j.25. So y11 would be what, minus j4. Your z12 is j.1. Therefore your y12, small y12 would be minus j10, which is also equal to y21. Again, you see that bus 1 is not connected to bus 3, right? It is, I mean, series network. So therefore your y13 would be 0, which therefore you can find out this y11, right, which is the sum of this. So y11 is minus j4, and this j10, it comes out to be minus j14. Now you don't have any shunt element corresponding to y22, therefore your small y22 would be 0, and your z23 is minus j4. So it y23 is j2.5, which is also equal to y32. Therefore, your y2 to capital Y22 is minus j.5. Just be careful of the plus and minus symbols, huh? Because if you, I mean, do a mistake here, you may get a different answer. For example, if you accidentally write it as minus, it would be coming out to be 12.5, which is also there in the option, right? You may click, selected a wrong answer option. And in the same way, you get this y3 also. It comes out to be J12.5. Now, when you put all these values here, it comes out to be your option number B. So this was problem number 9, which was pretty simple. And now this is a pretty interesting problem. So they have told key the inductance and capacitance of a three-phase 50 Hz lossless transmission line at 1.25 millihenry per kilometer per phase and 0.1 microfarad per kilometer per phase respectively. So the sending end voltage is maintained at 220 kV. Now to maintain voltage of 220 kV at the receiving end, when the line is delivering 380 megawatt, the shunt compensation required is, these are the, I mean, whether there is a shunt compensation required, and if it is required, what type is it? So for solving this, you have to calculate the surge impedance loading. So for this, you first need to calculate the surge impedance, which is nothing but root L by C. I mean your inductance divided by the capacitance. It comes out to be 113.14. Now you calculate the surge impedance loading. It comes out to be 427.8. Now I mean there is a I mean notation which is followed here. So your load is 380 megawatt, right? Now if the surge impedance loading is greater than your PL, which is the load power, the line generally behaves like a capacitive load. So to compensate it, you require the opposite of capacitance, right? So in capacitance, current leads the voltage. You require something opposite to it. So you require a inductive shunt compensation. So which is your option number C. So you just need to remember this kind of thing. So if the SIL is greater than PL, then you require a shunt inductive compensation, and if it is vice versa, you require capacitive compensation. So yeah, this was it. So mm, this was for I mean this was some of the typical problems of assignment 6. I hope this was clear.
Yes.
Okay. So, Lakshmi, I had mailed to NPTEL regarding the calculator thing, and they did reply me back. So they told that unfortunately the calculators won't be allowed in the exam, and you need to use the virtual, I mean, on-screen calculator, which is present over there.
Okay. Okay. Then so they are not going
What
to consider it.
Yeah, they are not
Okay.
going to consider it.
Okay.
What you can do is that, so I have a suggestion for you. So you can, just a minute. Yeah, you can download this Gate calculator. So if you are carrying an Android phone, you just search in Play Store Gate calculator. You can download that app. So it is similar to the virtual calculator only. I mean, ditto same, exactly same. I mean, you can practice using it while solving this kind of problem. So I mean, you will get somehow habituated and won't be having that much problem in the exam. You
Yeah,
can
I will
download.
try that suggestion. Yes. Here NPTEL also shared a link, TCSION, I guess. That is the link for a calculator. During the registration of exam itself, they have shared the
Yeah,
link.
TCS Ion. Yeah, yeah.
Yes. Okay,
I
I'll
mean, you
start
can
to practice that
download
one.
it in your mobile phone only. I mean,
Ah,
so what we used to do is that, so for GATE exam, we had to use that calculator. So teachers told us not to use the general, scientific calculator and try to download that app. And so we used to
okay.
use that. You may try that. It will somehow reduce your problem during the exam to some extent, I hope.
Okay, okay. Thank you. And in this chapter, I just have one doubt. Like
Yeah.
this load flow analysis we are seeing,
Hmm.
Gauss Seidel or Newton-Raphson, whatever. Uh,
Hmm.
Here we are mostly discussing about or taking the initial condition as pi model. Don't we do for long line model how it will be there, or generally the analysis happens, the power system analysis happens considering on treating everything as a pi model only, because whatever the derivation given for Gauss Seidel as well as the Newton Raphson's, it considers the y by 2 on both sides, the pi model only it is considering. So why aren't we considering the long line and other models? Is there any model for it?
See, I mean, as far as I know, your long transmission lines, those are basically distributed parameters, right? So for solving that, you need lumped parameters. I mean, you have to consider small sections of that line. And I don't know, I mean, we can also consider a T model also, because pi model and T model, both of these are pretty standard things. We can consider T model as well while solving this kind of problems.
Okay, because whatever I have seen the derivation and the problems, all of these items are pi model
Yeah.
related, and nothing is even short line as well as nothing is
Hmm.
long line also. So the derivation basically happens, and this model itself, because derivation gives the final output of formula, the admittance matrix, everything, and the y1112 and its signs and all totally depends on the model itself. It's applicable only for pi model. If I changing that to other model, then I don't know, the signs may change, the value may change, the matrix the matrix values would also change. So we are only doing for pi model. That is what I was thinking. Why don't we have it for other
I
kind of
don't
model,
know. I
when mode
mean,
52 for 500 or 600 kilometers line? Do we change that or assume that as a short, I mean median line, like a pi model? We will convert that and then we'll be doing the activity. How we will do it? Otherwise, because there is one more chapter I have seen where we are converting the long line model to equivalent pi model. So
hmm.
I mean, otherwise we will be converting a long line model into equivalent pi. The long line impedances will be converted into equivalent pi impedances, y by 2 and z, and then it will be converted or studied using this model. I don't know. So that was the thing I was having a doubt.
So I don't know. Pi model, T model also we can use. And for, as I told, for distribution, long transmission lines, you can't, you know, I mean, you have to also pi and T. All of these are steady state models, right? And whatever is happening in the this long transmission lines, these are all transient. So uh, I mean, they consider a small section of that line, find out the steady state model, which may be represented by the pi model only. I mean, that is why they are using this. But we can also consider T model also and solve the problem.
Okay, okay. And
Yeah.
one more thing, it's not a doubt. Last
Hmm.
session, right? Session number week 5,
Hmm.
the file that was uploaded in Google Drive folder,
Yeah.
that's not a proper file. It was the file of the previous session, week 4.
Okay. Okay. I see. Okay. Fine. I'll. I mean, correct that immediately. Thank you. Thank you. Thank
Yeah,
you.
okay. That's
Okay.
all. Thanks then.
Yeah. So okay. Fine. We'll then meet again next week.
Yeah, okay. Thank you.
Bye.
Bye.